So I would like now to resume part 2 of the narrow escape time in dimension 3. So we have seen that to calculate the mean first passage time, we needed to get an expression for the Green's function, which is rewritten here, Laplacian n equals minus delta Dirac plus 1 over v, and the Neumann boundary condition on the total boundary of the domain. So n can be expanded, can be written as a singular part where we have the highest singularity here for one of the points belonging to the absorbing, to the entire boundary, plus here a second term, which when we are dealing with the Dirichlet boundary condition has no singularity. So because of the Neumann condition, we'll see that it has a log singularity. And for this, we are going to write an equation for R. So this proof follow the Popov approach of 1992. This, I'll give the precise reference at the end. So what is the equation satisfied by R? We just need to replace R here in this equation. So because the delta Dirac is the solution of Laplacian of 1 over R is solution of the delta Dirac, we'll get that Laplacian. So we can use here for deriving the equation actually the case where y and x are in the domain. So x and y are in the domain omega, such that we are going to use actually the Green's function, the representation for which here, instead of having 2, we'll get the 4 pi. So everything will cancel out in the delta Dirac. So Laplacian R, so Laplacian n plus 1 over 4 pi, so Laplacian R plus 4 pi x minus y by definition is equal to minus delta Dirac plus 1 over volume, so which leads to Laplacian R equals 1 over volume. And now we have to calculate the derivative with respect to the normal. So dn d normal equals, so the derivative is dr d normal plus 1 over 4 1 over 4 d dn of x minus y cube x minus y multiply like x minus y, that's it. So yeah, multiply by normal. So this is already with the calculation of the normal. And by definition, this has to be equal to 0, which gives for R a condition. So yeah, actually what we need is to do the calculation for y. So let me redo what I've said is correct. I'm just now going to take omega in this absorbing part. So I'll go back to what I said previously. Instead of 4 here, we'll get the 2. So we have now derived partial differential equation for R, and we can use the Green's representation to express R as a function of n. So again, using Green's representation, which we have written, so let me write it one more time here. So n, Laplacian n multiplied by R. So if we integrate this, minus n Laplacian r over omega equals the integration over d omega of r dn d normal minus n dr d normal. And this is dv and this is ds. So with this, we can now look at each term separately. So Laplacian of n is simply Laplacian of n, this is simply minus delta Dirac. So Laplacian of n will give us minus r, so which we will write y and z at point y and z, plus 1 over volume of the integral of r minus n, so Laplacian r is exactly equal to v, so this will get minus integration of n, and this now equals the so the term on the boundary. So dn is 0, so this is going to cancel out, and we are left with n dr dn. So this is equal to minus integral of n. So let's write it x and y multiply by the term on the boundary, which is 1 divided by 2 pi of x minus y multiplied by normal divided by x minus y cube, and this is dsx. And now we can use the expression of n, which is simply equal here to 1 divided by 2 pi of 1 of x minus y plus r of x and y. So this is the an integral equation in R. And so what we are going to assume is a formal asymptotic expansion of x and y, which says that R equals R0, which is the leading order term, plus R1 of x and y. This is in the sense of Poincaré, where this says that R1 is more regular than R0. So basically we expand with the highest singularity, in the sense that the ratio of R0 divided by, or R1 divided by R0 has to be less singular than R0. So if we do this, then we can get from this an equation for R0, because this is going to be a regular function. So we will have here the only term that will remain is R0. And then we will just take from the right hand side here the most singular term, which is simply the first term here, the leading order singularity. This is this one. It will be multiplied by this one. So in effect, this leads to the following equation, that R0 R0 of y and z equals the integral over the boundary. So 2 pi multiplied by 2 pi leads to 4 pi squared. So 1 divided by 4 pi squared of the leading order singularity, which is x minus y, multiplied by the x minus z dot normal divided by x minus z cube ds of x. So this is now the term that we need to estimate. So we will assume that z is on the boundary. And we now assume some condition about the boundary, that the boundary has to be smooth enough so that it has a normal. But more than this, we need more regularity so that we can have a representation locally at what happened near z. So let's assume here that z is 0. Okay, this is the origin. And we assume that if we have the coordinates x1, x2, x3, that locally we have the following expansion of the surface. So 0 is, so we put the plane, the tangent plane at z equal 0. So basically we have to imagine that we have a surface like this. This is 0. So this excludes all kind of irregularity, cusp, and other singularities that we have treated in a different class. So let's assume that this can be written in the first term that are not 0, which is generically the second order term, is L divided by 2x1 squared plus n divided by 2 x2 squared plus something negligible. So this is the local representation of the surface. So now what we need to calculate is R0 of y and 0, which is now the integral of the normal multiplied by x dsx. And now, so z equals 0, so we have x cube, which is represented in x1. So x is in the coordinate of the surface x1, x2, x3. So we have x1, so this is the norm of x cube. So this is x1 squared plus x2 squared plus x3 squared, and this is to the power 3/2. And now we simply have to look at the difference of x1 minus y1 squared plus x2 minus y2 squared plus x3 minus y3 squared. And all of this is to power, so let me put it in red, this is to power 1/2. All right, so we need to calculate this quantity, and for this we can express the surface element dsx, which is simply given in terms of the norm of the normal. So this is classical differential geometry, which is 1 plus gradient of f squared, and then this is square root of this dx dy, and just using a differentiation of df, we'll get this is 1 plus 1 plus L squared x1 squared. So this is L squared x1 squared plus n squared x2 squared plus n squared x2 squared, square root of everything, multiplied by dx1 dx2. So this is dx1 dx2. So now we can also dx1 dx2. So now we can continue with the scalar product, which is n normal. So this is nu dot x, which is L x1 squared plus n x2 squared minus x3 divided by the norm of the normal, which is L squared L1 squared plus n squared x2 squared, square root. And finally, we can use some polar coordinates to write x1, x2, x3. So we'll write it r cosine phi, r sine phi, and then using the representation of x3 as a second order in x1, x2, this will simply be L r square sine phi squared divided by 2 plus n square r square cosine phi squared divided by 2. So I think we end y, we can have also y1, y2, y3, which is represented as the norm of y. So this is sine theta cosine phi 0, sine theta sine phi 0, and the last coordinate is simply cosine theta. So now we are ready to write what is r0 of y and 0. So this is 1 over 4 pi. And now we are going to integrate, because we don't have to integrate over the entire surface, because the singularity only occur when y is close to 0. So this is the integral from 0 to a of the integral of phi from 0 to 2 pi. So the surface element is 2 pi r dr. And now we have to use the normal, the nu dot x, which is exactly what we have calculated here. So this is L, so x is r squared cosine squared phi plus n squared plus n x2 squared, which is r squared sine squared phi. So this is nu dot x, and then we have to subtract minus x3, and x3 is this L squared divided by, so this is L divided by 2, multiplied by r squared cosine phi squared. So why do we have here? Yeah, so this is the opposite. This is cosine here, and this is sine here. So r squared cosine square phi minus n divided by 2 r squared sine square phi. And then now we have to divide by, so we have x, the norm of x to the power 3/2, so this is simply r squared to the power plus a negligible term to the power 3/2. And then we have now to calculate the difference x minus y, so we can use this difference here. So now I'll leave this as the calculation. So this is r squared plus y squared plus y squared. This is the norm of y. Minus 2r, so minus 2ry, 2ry sine theta, multiplied by cosine of phi minus phi 0, plus r squared, so there is another term here, plus r squared norm of y. And everything is to the power 1/2. Right, so this is everything here is to the power 1/2. So this is simply what we have shown previously about x minus y squared, which is again computed from just looking at the difference here between these two quantity x here and y. Okay, so let me erase this. Okay, so now we need to calculate. So to calculate more specifically this quantity. So for this, we need to estimate all of this, right? So for this, we note that we can calculate now with respect to phi, and so let's write this integral. So we will write now the integral. We will first integrate with respect to a, and then with respect to phi. So let's write it this way. We have r0 of y and 0, which is 1 over 4 pi squared, integral from 0 to 2 pi. So we can now get out of the integral the term that does not depend on a, which is cosine phi squared, plus n divided by 2 sine phi squared. And then we have to integrate from 0 to a of the term which is everything which was in the denominator. And this actually can be integrated. So this term here can be actually fully integrated, and it is of the order of log of a minus y. So this I leave as an exercise: sine theta cosine phi minus phi 0 plus a squared plus the norm of y minus 2a norm of y cosine phi divided, and so this is square root here, divided by norm of y, and then we're left with a term of 1 minus sine theta cosine phi minus phi 0. And actually this is of the order of log of 1 of y, 1 over norm of y. And so now we can do the integration over, in the leading order term, we neglect here all dependency in cosine phi. And so we can now just calculate this d phi, which is only the integral here, which will give us the following expression. This is L plus n divided by 4 pi, and then we are left with log of 1 over this, which is in reality log of 1 over y minus z, because z was 0. So this shows that the second term in the expansion of R is a log term, right, y and z, and this is the normal at z. This is the first and the second curvature at the point z. Z is in d omega. So then we can now use the expansion of the Green's function is now n of z and y, which is 1 over 2 pi of z minus y plus lz plus nz divided by 8 pi log of y minus z. And so what can be shown is that there is here an order 1 term. There is no singularity in this term. So this is in dimension 3. So this is of order 1, and actually some more information can be computed from this, and I will give reference toward the end. So now we can use this Green's function to go back into the mean first passage time equation. So let's go back now to, so in the mean first passage time equation, so the computation of the narrow escape time. So we had to calculate this integral equation, which is the Neumann's function multiplied by the flux, which has to be equal to a constant for all y. So this is dsx for all y in this absorbing window. So now those 2 points are on the boundary. So now we can use this Green's function expansion, which is 1 over 2 pi plus 1 over 8 pi multiplied by the curvature, which we call hy, log of x minus y. So multiply by the flux g of x dsx equal to this constant. So now we can again make a flux representation in terms of g of x equal j0 of x plus j1 of x, which is again an expansion, a formal expansion, where j0 has the maximal singularity and j1 is more regular than j0, and so on. So if we use this, and we have already found that the flux for the, we can rewrite the flux J0, we know exactly what it is. It is 2c divided by a pi, this we calculated before, of 1 divided by r squared divided by a squared. So this is the exact expression for the flux. So now we can use this expansion in here, expand, and find an equation for J1 using the most important singularity, which is this one, leading to the following equation: 1 over 2 pi of x minus y multiplied by J1 of x dsx. If we integrate this, then this is equal to minus j0 of x, and now we have to use the other term, so the term c cancel out by definition, and this is h of y divided by 2 pi multiplied by log of x minus y dsx. So we now can use actually an expansion. So this is over d omega a. So we can use an expansion to write this. So this can be written of the form minus c L0 plus N0. So we assume that y0 is the center of the hole, divided by 2 pi a log of a. So this can be, so this is a result from a direct calculation by replacing here j0 in this integral and calculating directly using the coordinates, the local coordinates. So then J1 satisfy now the same type of equation as J0, because this is the same type of integral equation using this kernel, this 1 over x kernel. And so now we can do the same calculation, so I will not do it again. Just I refer to the first part. So J1 of x simply becomes minus c of L0 plus N0 divided by pi squared of 1 divided by r squared divided by a squared, square root. So this is the form of the flux multiplied by log of a. And so the total flux J of x is simply J0 plus j1 of x plus other term that we have neglected here, plus term that we have neglected. And so now we can write the mean first passage time, tau, which is by definition the constant c that can be calculated from the compatibility condition. So now we can use how to calculate the constant c. We use the compatibility condition, which say that j0 plus j1 has to be equal to minus the volume divided by the diffusion coefficient. So we have the constant c, which is unknown here. There was a constant c that is unknown here. And now by calculating this over the omega a, this is ds, by calculating this quantity, we can now finally get the mean first passage time, tau, which is this constant c equals to omega divided by 4ab, 1 plus the mean curvature at 0, which is the center, divided by 2 pi a log a plus a log a small term, negligible term. So this is the expression of the mean first passage time for the second order term. So now I'll give you some comments on this. The calculation here use the initial one described by Popov in 1992 in this reference. The third order term can be found in this reference. The case of the calculation inside the ball was already given more than 6 years ago in the books of Kellogg's as an exercise. The precise calculation that I've used here has been published in this 2008 paper of narrow escape and leakage of Brownian particle. And the summary of all of this can be found in our new book.